Today's lecture is going to be on forces acting on ships. So when we talk about forces acting on ships, we have a couple of different types of forces that we're actually talking about. So we have our uncontrollable forces, which include wind, current, and waves, or environmental conditions in general. And then we have another type called our controllable forces. Now these are things that we have active and complete control over, like the position of our rudder, how fast we're turning our propellers, if we have bow thrusters, how much we're using those, tugs, mooring lines, of course, can be different types of forces acting on our ship, and ground tackle, which is our anchors and chains. We also have something called semi-controllable forces. And these items are items that we know are going to affect our ship depending on how we operate and where. So when we're talking about bow cushion, the faster I go, the bigger my bow cushion is, and I know it's always there. So although I can't completely control how it affects my ship, it's a very understandable and repeatable process for the most part. Same with bank suction and squat. And we'll talk about these things a little bit later on in the lecture. But to sum it up, if I am close to a bank and I'm proceeding at a certain speed, I'm going to have a certain amount of suction force that's going to want to pull me into the bank. Now the faster I go, the more of that suction force is going to happen on my hull. And the same thing is true of squat. So let's just talk about general forces acting on ships. And you can see this picture shows a ton of different forces that you can see. So we have turning moments based on the rudders. So down here we've got some rudders. Our ship has some drag as well. Thrust from the propellers is huge, so I can do that in a forward or a stern propulsion. I've got current can act on the side of my ship, the front of my ship, so can wind. The Bernoulli effect, which is what is going to give us some of our suction effects when we get to banks. I've got stern walk in either direction, depending on which direction I'm going and the way my propellers are set up. I've got this guy right here, which is tension from an unrep rig. So this could mean another vessel is trying to reprovision my ship and has a tight wire that goes from what's called a king post on my ship to their loading gantry. Now, these unrep rigs are typically for vessels over 270 feet. You're not going to see this on smaller vessels, but it gives the ability to take dry goods as well as fuels over to another vessel that's on some sort of long leg and can't get into port to help actually reprovision. But in order for any of these forces to make sense to us, we need to be able to put them in terms of a moment. So I need to know where I'm pivoting from. And now this changes throughout the speed process of my ship. As I speed up, my pivot point is going to move, and the same is true as if I slow down. So if we look here at this image, I can see my vessel dead in the water and just starting to come ahead. And at this point, this X area here is where my pivot point is. As my vessel starts to move forward and becomes steady state in its speed, which means it's going at a constant velocity, it's no longer accelerating, my pivot point moves to about 1/3 the distance from my bow to my stern, so about 1/3 the length of the ship. The same is true if I'm going astern. When I initially start moving in astern, my pivot point is right at this stern. As I begin to gain sternway, my transition is going to be for it to move forward on the ship until I get to a steady state based on my velocity, which is normally about, like I said, and this is a rough estimate, about 1/3 of the distance from the stern, and that'll be my pivot point. Now, we talked about some of the other forces that actually act on my vessel, and here we have a vessel moving ahead with a line being held. This is a mooring line. Now, typically if we have mooring lines, or even down here with my ground tackle, we're going to say my pivot point is where this hard fixed item like a line or a chain exits the hull of the ship, and that's where my pivot point is going to then transition to. So no matter what's happening here, so normally a vessel dead in the water would have its pivot point up here. However, since I have a mooring line over and I'm actively thrusting with my propellers, my pivot point is said to act right where my mooring line exits the ship. The same is true of my ground tackle or my anchors. In order to kind of show the idea of a pivot point, we're going to use this graphic. So the first one up top here shows a vessel that is stationary. It has two tugs pulling down at equal force. So what I know is that my distance between these two is equal. my force acting down in this direction is equal. So this vessel is going to move straight in this direction without changing its overall orientation. Okay, so now we're going to change that a little bit and say I've got a vessel moving ahead. Now my vessel's moving ahead, and I still have these same forces acting down by my tugs. Now notice the difference is my pivot point has changed. My pivot point is no longer right here in the middle. It's up here. So this is my pivot point. So what do we know now? I know that my lever arm is different now. Same amount of force being pulled down, but a smaller distance up here than I have here. So this moment here is actually going to be greater, and it's going to cause my stern to come in. So no longer will I have a nice horizontal orientation. My vessel is going to move in this direction as well as being moved in this direction. The same is true if I'm going astern propulsion. Again, my lever arm in the front now is longer than my lever arm on the stern. And because that lever arm is longer, but my forces are still equal, I'm creating a higher moment on the forward part of this ship, and it's going to cause my vessel to come in this orientation as well as down towards the bottom. So you can see how the pivot point shifting while the vessel is moving can change the orientation and might have to change how you use these external forces if you're trying to keep your vessel completely parallel with, let's say, a pier face or another vessel. Turning. So turning is another great way to see the pivot point transition. As I increase my speed, my pivot point starts here and moves backwards. And you can see originally this vessel was tracking on a pretty decent turn radius. As it's coming back, my pivot point's going to move back here, and the reason that my pivot point doesn't move to the middle of the ship has a lot to do with a lot of these forces that you see acting along the hull. So as I'm pushing my rudder over to the side, I'm creating a high pressure area over here because I'm basically piling all the water up on top of itself. At the same time, I'm creating a vacuum over here. So not a pure vacuum. I'm not creating a vacuum. What I'm doing is creating low pressure. And I'm doing the same thing up on the bow, only in the opposite direction. I'm creating, as this is pivoting through, I'm creating low pressure up here and high pressure over here. So the vessel is having to fight all of these forces as it's coming through. And this is how we can determine what our overall turn radius is. So this underwater body shape of our ship will dictate how much we're being affected by these forces, and therefore dictate how quickly we can turn based on the hull form that's below the waterline. So we look at wind. Wind is something that always affects our ship. And we're looking at our equation up here, and we see a couple values. I see a value for area. Now this area is going to be the area exposed to the wind when the wind is acting at 90 degrees. So I see my wind acting here. That is not at 90 degrees to my vessel's either forward portion or beam portion. So what I have to do is break this wind into its X and Y components, with my ship being the axis. So this wind has two components here. It has my X and my Y. I'm going to break that wind up, find out what the overall velocity is in the Y direction and X direction using my sine and cosine conventions, and find out what this velocity value is. Once I do that based on sine and cosine, that's where my V value becomes relevant. Okay, so if I'm talking about a headwind, now my area is going to be the area of the front of the ship. So if I look at a normal ship, it looks something like this, right? But some portion of that is underwater. So I'm not concerned about the underwater portion. I'm concerned about this area that's being exposed to the wind. And that would be the area that I'm going to then input into my equation to find out what the force of the wind is acting on my ship. I'm going to do that again for the beam wind. So now I have this value here, and I know if my ship typically looks like this, some portion of that is underwater. So the area that I'm talking about is everything that's above the water, but only in the profile view. I'm not worried about curvature. I'm just worried about what face is being presented to the wind. And that's how I determine what the wind force is acting on my ship. As you can see, this vessel continues to get pushed, and because, if we go back one slide, because this vessel has a large amount of sail area on the beam over here, it's going to continue to get pushed both down and to port. And you can see that happening in this graphic here. It gets down into port until it gets about to beam to. Alright, if we look again, this is just another example of the force of the wind, only it's important to understand where this wind force is going to act. This isn't just a single point load, it's acting across the entire surface area of either the beam of my ship or the forward portion of my ship. So I need to find the centroidal position of that wind or sail area. It's called sail area. And in this case, I've got more sail area back aft than I do up forward. So we're going to say that wind is actually acting right here, which would be the center of that area. Where's my pivot point? Well, it's just forward of that. So as the wind hits, this vessel is going to want to turn to port. So this is actually creating a moment. So if I have the wind pushing, assume we're acting at the center of the area, and the pivot point being here, well, this vessel is going to want to turn in this direction. So we're going to have to add some weather helm. But we'll talk about that a little bit later. So now I take the exact same scenario, and I have my vessel moving forward. So before my vessel was dead in the water, my pivot point was here. So I have a relatively small lever arm, so my vessel is going to continue to rotate in the direction that that lever arm is acting about. Well, now my pivot point is way up here, so I have a larger lever arm. My force of the wind hasn't changed in this beam condition, so I'm going to have even more of a turning moment created by the wind here. So we can see, in this case, moving forward is actually giving me more turning moment from the wind. So I can see here these two different forces acting on ships based on the wind speed. So I've got a relatively low wind speed, I've got no force. As I continue to increase the speed of the wind, I have more and more force acting on these two different types of vessels. Now if we look, this car carrier here, this is a much more steep climb versus this oil tanker. What's the difference between the two? Well, it has everything to do with freeboard. So how much, and freeboard, not only just freeboard, but my overall air draft, like how much is exposed to the wind. So if I look at these two types of vessels here, as we zoom out, I can see this guy here corresponds to the steeper curve, because look at all of this sail area here. And this tanker, it's going to creep up a lot less quickly because it doesn't have as much sail area as the car carrier does. So it's important. This area is not a squared function, the wind speed is, however, it can be a large driver as to how quickly you're going to be affected by these forces. The next part of it is current. Now current isn't any different than wind except for it has a lot more effect. Water is not compressible, it's more dense than wind is, so as our wind is affecting us, we saw we had a different value that we were multiplying at times. So we were looking more along in the category of a 0.0034 instead of this 2.85. Well, that's because current actually has more of an effect on our vessel than wind does. So as we move through and we do our currents, we're going to do them the exact same way as we did with the wind, only instead of using the exposed portion of the vessel like we did before, now this is our frontal area. Same with the side of the ship. Our area underwater, this is the area we're concerned about. We still have to find the resultant force if we say we have a current acting upon us, but that's okay. We can do that using trig. Something interesting about this case, though, is as I go faster, the current has less of an effect. So think about this as sitting stationary for a while and drifting in the water. If I'm drifting in the water over a period of time, my vessel's sitting here, if I clock that time, it should be a certain amount of time is going to get me a certain amount of distance. Distance equals rate times time. So if I allow this current to act on my vessel, I'm going to have, over a longer period of time, I'm going to have more of a cross-current push. So it's going to push me further and further off track. Now the faster I go in this direction, it's going to push me less and less off track. And this is a function of the fluids that's actually happening on the hull of the vessel. And I can see that the speed over ground of 5 knots, over the same period of time is going to decrease my overall resultant drift due to current. So, all right, so what are we talking about here? We're talking about Eagle. What do we have on Eagle? Well, weather helm or lee helm, that's the discussion. So what's the difference? Weather helm is when a vessel wants to turn into the wind. So if I have a vessel whose pivot point, so here we're going to use a barge, and let's say I have a pivot point here, but its sail area, and this will be the bow in this case, its pivot point is here, but its sail area is centroid of that is actually back here. Well, the wind is going to want to push my bow in this direction or back into the wind. So I'm going to have to use some amount of rudder to keep my vessel from doing that. And of course, if the wind is coming in this direction here, in order to counteract this moment that wants me to go in this direction, my rudder is going to have to act in this direction to give me some amount of moment that will counteract. So we've got to figure out what that is. Lee helm is the opposite. So lee helm is more common on our traditional Coast Guard vessels because they tend to have a lot of sail area up forward. And I have my pivot point here, and I'm going to have, well, let's put it here, and I'm going to say this is where my centroid of my sail area is. Well, when I do this, my cutter or ship is going to have a tendency to fall off the wind. And that's when I would have to use lee helm, so I'd have to put some amount of rudder in this direction in order to maintain course and speed. Important distinctions when you're on the helm of a vessel. Crab angle. So we saw from these different types of currents and wind forces here that we're going to have some environmentals that are pushing us off course. So how do we stay on course? Well, we figure out what that equilibrium point is with our vessel, and we put our ship into an orientation that gives us a true course over ground. So even though I'm pointing at this heading here, my vessel, because of the environmentals pushing it, is actually traveling along this line and keeping us on range. This is huge. This is my course over ground versus my heading. So I can head directly into the wind and actually go nowhere. So if my vessel was head into the wind right here, and I was going at the exact, and I was thrusting my propellers at the exact same amount of force that the wind was acting on my bow, I would go nowhere. However, now I don't want that to happen. I want to use this course. So I'm going to slightly alter my course so that I've got the wind off my port beam and my vessel is capable of tracking on our desired course over ground. We're basically stemming the currents. We're making sure that our environmental conditions are pushing us in a way that's predictable for us and that we can maintain our course. We do this all the time entering ports. And it's going to change throughout the transit. As we continue on our transit, we're going to see that we have to change our rudder or our crab angle in order to maintain a certain course. And this is due to the land masses and the water currents being affected, the land masses affecting our wind and our currents differently as we progress further and further in port. So this is a constant adjustment. There's another thing called blanketing, and blanketing can either block the wind or the current. In this case, we're going to say we're blocking current, and we're going to say that this entire face of the pier here goes all the way down so that we don't have any amount of current actually sneaking underneath this pier face and affecting our ship. As this vessel starts to back out of port, you can see it's backing up perfectly straight. It's backing straight down, rudder amidship. But as soon as the stern gets exposed to this current here, this amount of area, right, is being exposed with a pivot point right there, and we're operating in a stern propulsion, so our ship's pivot point is right here. This is where the current is acting. It's going to create a moment that's going to move our ship in this direction. And as we expose more and more of that area, we can see the effect lessen some and actually maintain the same orientation that we had before. Now, as we continue to expose ourselves to this current, and maybe we start changing our engine orientations to the point where we're dead in the water, we might see some sort of current effect change and continue to push us in the direction of rotation we were in before, such as what just happened here. So another example would be a vessel moving ahead in a channel. Now we're going to say this is our wind. So we have a heavy wind that's pushing in the direction of the arrows listed here. This is a buoy, a floating buoy, and this is a floating buoy. What's happening at the bottom? Well, this buoy is actually attached by a bunch of chain to a sinker, just as my starboard marker is as well. Now, if I have a lot of wind, these guys are actually going to be not directly over their sinker as I've drawn here, but they're going to be closer to this. The wind's pushing them and the chain's holding them in place. So what happens as my vessel moves further up the channel? Well, it starts to mask the wind, and the buoy starts to bring itself right above its sinker because it's not feeling any of those forces due to the wind. And if I'm not careful, and this comes back to where it wants to be, and I don't predict this happening, I could actually have the buoy strike my vessel, and that's no good. So let's do a calculation here. We've seen how we can be affected by the wind and how other things can as well, but in this example we're asked to find the rudder force needed to maintain a heading. Our pivot point is our smiley face, and it's located 20 feet aft of the bow. And we're saying that the center of area for our for our underwater body is 30 feet aft of the bow. So let's figure out what kind of rudder force we need to counteract this. In order to do it, we need to figure out that our force of our current times its lever arm, which is going to be 10, has got to be equal to the force of the rudder times its lever arm, which is all the way at the stern, so it's this 80 value to the pivot point. Alright, so I figured that out. This is what my equation is. I have two unknowns. I don't know the force of the current. I don't know the force of the rudder. I can figure out the force of the current, though, because I have an equation for it. So the force of the current is equal to 2.85 times the submerged area, and in this case I'm worried about the submerged area exposed on my beam because we're trying to figure out how much rudder I need, times the velocity squared. Okay, so how do I do this? Well, I know that I need to be able to figure out what my velocity squared is. We also need area. My area of my vessel is my length, so that's 100 feet, times my draft, times 12. So that's my underwater area, and that equals 1200. So we figured out A here. Let's figure out our velocity. We're given a value of 4 knots, but we know this isn't true. I need to use my sign convention here. So my velocity is equal to 4, because that's our knots of current, times the sine of 30 degrees. And 30 degrees is given. And that's going to give me my y component in this case. Now I can plug this v value that I get back into here. When I do so, I get a value of, and I plug my area back in, I get a force of the current equal to 13,680 pounds. Sweet. So now I have my force of the current. I can put it back into the equation here and figure out what my lone unknown is, which is the force that I need on my rudder. If I do the math, force on the rudder ends up equaling 1,710 pounds. Why is that so much less than the force of the current? I have a larger lever arm for my rudder than I do for my current, so I need less force because I have more distance. Great. So I figured out how much rudder I need because I figured out how much side force was acting on my ship based on its pivot point and what type of moment that was creating. Now I need to know how much power I need to create to maintain my speed. So all I really need, I need to know the force of my propellers has to equal the force of the current. So I want to maintain speed. I'm not trying to accelerate, so these forces are going to be equal to each other, which makes it nice. So I can just figure out the current force based on my new values. And we already know 2.85 times the area. Now in this case, my area is going to be my beam times my draft, because I'm talking about the frontal area exposed, so the current that's acting in this direction in the x value. And I'm also going to, my velocity vector here, it was 4 sine 30 last time, it's 4 cosine 30 this time, and that velocity vector is squared. My overall value is 4,104 pounds. So that's how much additional thrust I need to add from my propeller in order to maintain my current speed. Alright, hopefully that was fairly straightforward. And we'll move on and start talking about some of the other parts of a ship and how they can be affected. So you can see here, this is for your own understanding and just edification what the bottom of a ship looks like. We have all these underwater appendages. This is a shaft bearing right here. Here's our actual propeller shaft that's coming out of the vessel. And here's a strut that holds our bearing and therefore holds our shaft and propellers in place. We would call these propeller blades, and if this would be called a propeller hub. You can also see the rudder back here as well, one of the rudders. There are two different types of propellers. There's many more than two different types. There's two different types of handed propellers, so the direction in which they're twisted around their hub. There's a left-handed and there is a right-handed. Typically, if you have a dual propeller ship, you'll have a left-handed and a right-handed so that they oppose each other, so you can minimize side forces as you're moving ahead and in a stern propulsion. Well, if you look below, we can see a single shafted vessel is going to have a little bit of what we call walk. So if I have a right-hand prop and I'm operating in a stern propulsion, I'm going to actually walk my stern to port and vice versa. So if I had a left-handed prop, it's going to walk the other direction when in the stern propulsion. And this has a lot to do with the way all of the water that's being shed off the propeller interacts with the hull, or a lot of those appendages that we saw in the last slide, because those exist for both a dual propeller and a single propeller ship. So we do have some amount of stern walk when we're operating these vessels in a stern propulsion. And here we have some rudders. Really the name of the game here with rudders is trying to get as much surface area inside the overall propeller wash area. We want to be able to move as much water as possible past as big a surface area as possible with as little obstructions as possible. We have some values, some different types here where your propeller would actually be housed inside of these. These are good. There's nothing wrong with them. They put the propeller right in line with the rudder, or the rudder right in line with the propeller, and they have a lot of surface area. They also create a lot of drag and a lot of non-laminar flow of the water into the propeller because of all the housing that's around it. So we have these other types of propellers which try and limit that, and these are more traditional. So Eagle would have something like this, whereas a typical cutter would have something more along the lines of these here, where it's just a shaft that's supporting the rudder and putting it right into the discharge race of the propeller. Rudders need water flow across them to work. So a setup like this, where our rudder is here and the propellers never really discharge anything over the rudders, isn't very effective. If this vessel is moving ahead, it's going to give it some water flow past it, but not nearly as much as if I put the rudders into the discharge zone or the discharge race. These give me much more water movement across my propellers and give me more turning effect for surface area. And typically our ships are designed in a way that will put these rudders right inside that discharge race to maximize the flow across them. Now, bow thrusters is another type of force that we call controllable, and this is just a picture of one. It's normally a big tube that operates through the ship, and we turn this propeller and allow thrust to either come towards us or away from us, and it helps us maneuver the vessel transversely versus longitudinally. So if my vessel is sitting here normally, I have propellers that want to push my vessel this way, and I can get some amount of turning action from my rudders, but a bow propeller will allow me to operate my vessel port and starboard depending on how much thrust I provide. And there can be stern thrusters as well as bow thrusters. Most cruise ships and large vessels have both. Some vessels have what are called azimuthing thrusters. Now these are basically propeller drive systems that have the drive shaft come in, come down, and then mate right here with this propeller. This gives the ability for this device to circulate 360 degrees. Increases maneuverability. You can point load thrust. You can direct it exactly where you want it. Super, super effective for maneuverability. And we typically will call these guys a Z drive because this little driveline shaft that I drew looks a little like a Z. So that's a Z drive. Tugs. Tugs are another force that we talk about, a controllable force. They can either push on us, they can pull lines. A lot of these things are very, very beneficial for less maneuverable vessels such as Eagle. The problem is, if they don't touch your ship in the right place, they could actually cause structural damage because they have a lot of power because their job is typically to move vessels larger than themselves. So you have to be careful how you use tugs and where they touch your ship and make sure communications between the pilot and the tug is good so that you don't end up damaging your ship during these evolutions. You can see here mooring lines and ground tackle. So mooring lines are here, ground tackle are housed up under this area. Those are where the anchors are. And we need to understand that there's a lot of tension on these items, these lines right here. And they're typically made out of synthetic material. This synthetic material can break and snap like a rubber band and create a lot of damage to equipment as well as personnel that are in the vicinity. But it's just important to know that my pivot point here, if I'm moored with this line and this line only, is actually going to be right here on my ship. So I need to understand how mooring lines and ground tackle affect my ship's pivot point. The ground tackle is going to exit the hawse pipe, come down and touch the bottom, and therefore my pivot point is here, or where it actually exits the skin of the ship. And this is what my ground tackle looks like. It's a big anchor with lots and lots of chain. So as we move on and we start talking about bow cushion and bank suction, we have a couple of interesting effects. As I move my vessel quickly through the water in this direction, I'm creating a high velocity flow of water here. Well, the faster water moves, the lower pressure it is on that side. And the reason is because, why is it moving faster when I have a bank over here? Well, as my ship moves forward, it's actually leaving a hole in the ocean that water has to quickly fill. Well, as I move past this bank, the water, the hole that has to be filled from this side can pretty easily just fill in. But it has to do this on the other side too, which means the water actually has to race in much faster because there's not as much of it over here because of where the bank is. Move much faster in order to fill this hole that my ship has created. When this happens, I create a bank suction effect. Another thing happens too as my vessel moves through the water is that I create a pillowing effect of water here. As I push through, it tends to stack up on itself and create what's called a bow cushion. Now this bow cushion is going to have the opposite effect of the suction. It's going to actually want to push my bow away from the bank. At the same time, my bank suction is going to want to pull my stern in. So if I'm not careful, I can really quickly find my vessel in this orientation here, which is bad, as we learned from our previous two discussions on grounding and keeping your vessel out of those situations. Squat. Squat is the exact same thing as bow suction, only it happens on the bottom. As I transition from deep water to more shallow water, the hole that my ship is leaving in the water has to be filled more quickly again, and I don't have as much room for the water to, or as much volume for the water to quickly fill in that hole that was left. So that means water has to move from up forward and then come in here, or from back aft and come in, which increases its velocity and therefore lowers the pressure and is going to cause a suction effect in that direction, which you can see here can end up with you touching bottom. So this would be a stationary ship, even keel, good to go. We start moving ahead at, say, 10 knots. All of a sudden, I've created a low pressure zone down here and have actually caused my ship to contact the bottom, and that's not good. Well, as we move forward, here's some different YouTube links you can look and see. These are some smaller vessels that are actually shown inside a water channel or a small river that show different types of effects from bow cushion and bank suction and squat. They're worth a look. You can put in those YouTube links right there and check those videos out, and it might help and aid in your understanding what's happening just a little bit. I hope you got a lot out of this lecture, and like always, do your learning activity and read the course reader.